Hello everyone, and we're going to continue our look at electricity and magnetism by thinking about how electrical energy gets used. And to do that, we have to think about what actually makes it run in the first place, and we mentioned last time that that is a potential difference. So, as we said last time, the potential difference is a difference in energy found at two different points in a circuit. And you can think of it like water running down a hill. So, the amount of water that passes a point would be compared to the charge that was passing a point, and the speed at which that water passes is going to be called the current, which is just what we would say with real water. A strong current has fast running water. And the thing is, the water flows that way, the water flows at all because of the gradient. It's going down a hill. So it's going from a higher point, a point of higher gravitational potential energy, to a lower point where there is less gravitational potential energy. So in a circuit, you just substitute gravitational potential with electrical potential. And that is the analogy of potential difference. It's electrical energy flowing down a hill, down a gradient. So this is the potential difference. So now if we think about a water wheel in our river, a certain amount of water passing a certain point at a certain speed is going to have the effect of turning that water wheel by a certain amount. And as you can see from this diagram here, it's going to represent work being done. You can take that change in gravitational potential of the water and turn it into work being done. And so you can take a difference in potential, in electrical potential between 2 points, and you can turn that into work being done. So after the water has fallen down, falls, it has less gravitational potential energy, and this means that there is less energy available in the system. The same thing can be found in an electrical circuit. After you have used some energy in a component like a light bulb, there is less potential left in the circuit after that point. And it's interesting to note the diagram here is actually a diagram of a real Roman age sawmill that existed as one of the first real complex machines that humanity was able to build. So it turns out this potential difference we've been talking about is exactly the same as a word you will all have heard, and that's voltage. They are the same thing, voltage and potential difference, and as we said, they are a gradient, essentially an electrical gradient that causes current to flow around the circuit. So, as a formal definition, a potential difference, which would be measured in volts, between 2 points in a circuit is the amount of work done, measured as an amount of energy, per unit of charge, and each unit of charge will be a measurement in coulombs. So that is the amount of work done per unit of charge that flows between the 2 points. So just have a think, how do you reckon this is going to be calculated, and what word brings to your attention how this is going to happen? So let's look at voltage, or PD, again. It's measured in, as we saw, volts, and in an equation the symbol we will use for voltage is going to be V. Yes, it's exactly the same. This is not always the case, as we've seen with charge, represented as Q in an equation and measured in coulombs, C. But with volts, it's the same unit. And the equation itself is V is equal to W over Q, which is equal to E over Q. And the W in this equation, as we saw before, is work done in joules. Q is the amount of charge passing the points, and E, what would E be? It's electrical energy, because an amount of work is done by a certain amount of energy, so those two things are equivalent. So let's have a look at a simple circuit diagram, and let's say that the electrons begin at the negative point with 20 joules of electrical energy. That is the potential of the electrons in that part of the circuit. So as they pass through the bulb on the left hand side, some of that energy will be converted to photons of light. Let's say that that's 10 joules of energy converted in that way. Let's say too that 5 coulombs of charge total have passed through this bulb, and the electrons that form that 5 coulombs of charge have less energy or less potential than they had before they went in. So despite that reduced potential, they are still moving, they have the same current, and they will continue to arrive back at the positive part of the battery. But what do you think the voltage is across the bulb in this circuit? And more or less across the whole circuit, because the bulb is the only component. Well, the voltage across this bulb is clearly 0, because the switch at the bottom is open and no current is flowing through this circuit at the moment. However, if we're not going to be pedantic, we could say that if they start with 20 joules of energy and they lose 10, so the change in energy, the work done going through the bulb to make light, is 10 joules, and to make that 10 joules we've had to pass 5 coulombs of charge. So we could say that 10 joules divided by 5 coulombs is 2 volts across the bulb in this circuit. And as well as being 2 volts, we could also think of that as being 2 joules per coulomb. So for every coulomb of charge that goes through that bulb, 2 joules of potential from that coulomb of charge are lost to light energy. So how do we measure voltage? Well, using one of these devices in a circuit, a voltmeter. And unlike an ammeter, a voltmeter must be connected at 2 points, which means it is connected across a component, allowing us to see electrical energy being used at different places around the circuit. An ammeter is put in a circuit and it measures the same current at every point on a circuit. However, the voltmeter is what we measure across possibly the whole circuit, or at least across individual components, to see how much electrical energy they are taking from the total. So let's recap. In a conducting material, we find a large number of free electrons, and these are known to carry a certain amount of charge, and the amount of charge flowing through a circuit is called the amount of electrical current that it has. So each unit of charge, and a unit of charge, or the SI unit of charge, is a coulomb, can also have a certain amount of electrical potential energy, or sometimes just potential. So the difference between electrical potential energy between 2 points is called the potential difference, and is otherwise known as a voltage. So that is the relationship between all of the vocabulary in what we've studied so far. So let's also look at the units we've considered. So you can be thinking about the units associated with all of these things: charge, time, current, electrical energy, and voltage. And not only the symbol that is used in the equation, but the unit symbol that is used when writing numbers as well. So with charge, the equation symbol, as we've seen, is Q, but the units are in coulombs, and so the unit symbol is a capital C. Time, we know very well. Its equation symbol is T, but it's measured in seconds or small s. Current is given the symbol I, and it's measured in amperes, which have a capital A, remembering that if the unit symbol is a capital letter, that often means that it's been named after someone. Electrical energy given as E, we've also seen it as work done W, but like all energy, it's measured in joules, which is given a capital J. And then finally, we have voltage. The symbol in an equation is V, and it's measured in volts, so the unit symbol is also capital V. Finally, we're going to have a look at the difference between voltage and current. So just to put them next to each other, because it's easy to get confused between the two. So the symbols we've already looked at, and the definitions just at the top there. Current is the rate at which electrical charge flows past a point in a circuit. So it's the rate of flow of electrical charge. So the voltage is a potential difference, which is the change in electrical energy between 2 points, and it's similar to the way that gravitational potential energy will change between 2 heights. And so between those 2 points there is a gradient, there is a slope in electrical energy, and that is what creates the current, that is what causes the current to flow. So it says there, in the relationship, the current is the effect of voltage, voltage is the cause of current. You can have a voltage with no current flowing. And just interestingly, we can see the way that they both contribute in different ways to the idea of electromagnetism, that a current creates a magnetic field, whereas voltage creates an electrostatic field. And this is how we see the two as separate phenomena, even though they are created by the same effects. And so that's where we're going to leave it there. You can see down the bottom there are some other entries for series and parallel connections. And you might wonder what those are. You might already know, but those are what we're going to think about next time.